In the time it takes you to watch this video, light from the most distant galaxy we've ever discovered will travel another 300 million miles toward us. But that light began its journey when our universe was barely 280 million years old, long before Earth, before our Sun, before the Milky Way even looked like it does today. We're about to fly through every single one of the 2 trillion galaxies in our observable universe. You'll witness impossible collisions spanning hundreds of millions of years, discover galaxies that shouldn't exist, and see cosmic structures so vast they make our entire galaxy look like a speck of dust. If you're ready to expand your cosmic perspective, hit that like button now. Prepare yourselves. We begin. Everything you think you know about how many galaxies exist is wrong by a factor of 10. Until 2024, astronomers confidently told us there were around 200 billion galaxies in our observable universe. That number felt impossibly large already. But when the James Webb Space Telescope turned its infrared eyes towards seemingly empty patches of space, it shattered that estimate completely. The real number? 2 trillion galaxies. That means for every single galaxy we thought existed, 9 more were hiding in the cosmic shadows, too faint and distant for our previous telescopes to detect. Think about this confirmed fact. In the time it takes you to blink, light from thousands of these newly discovered galaxies crosses another mile of space on its journey toward Earth. Some of that light has been traveling since before our solar system even formed. We are literally seeing the baby pictures of the universe, and there are far more babies than we ever imagined. The Hubble Space Telescope gave us our first hint of this hidden population when it stared at what astronomers call the ultra-deep field. This image required 800 separate exposures over 11 days, capturing a patch of sky smaller than a grain of sand held at arm's length. In that tiny slice of apparent emptiness, Hubble found 10,000 galaxies, 10,000 entire worlds, each containing billions of stars, crammed into a space that would be covered by the period at the end of this sentence if you held it up to the night sky. But here's where it gets truly mind-bending. That ultra-deep field represents just 1/13 millionth of the entire sky. Multiply those 10,000 galaxies by 13 million, and you start to grasp the scale we're dealing with. But even that calculation was conservative, because Hubble could only see the bright, nearby galaxies. Webb's infrared vision revealed the rest. Galaxies so distant their light has been stretched from visible wavelengths into infrared radiation. Galaxies so small and faint, they're like trying to spot a candle flame on the moon. Each one representing hundreds of millions or even trillions of stars, planets, and potentially entire civilizations we'll never know about. The math becomes almost meaningless at this scale. If every galaxy contained just 100 billion stars like our Milky Way, we're looking at 200 sextillion stars in the observable universe alone. That's a 2 followed by 23 zeros. More stars than grains of sand on every beach on Earth. And remember, this is just what we can observe. The actual universe extends far beyond our cosmic horizon, possibly containing infinite galaxies stretching in all directions forever. What we can see represents a tiny bubble in an ocean of space that might have no edge at all. But what comes next makes even these staggering numbers pale in comparison to the violence and beauty hiding within each of these cosmic islands. Right now, you're hurtling through space at over 1 million miles per hour, and you don't even feel it. You're not just spinning with Earth or orbiting with our solar system around the Sun. You're being carried along by the Milky Way galaxy itself as it barrels through space toward an inevitable cosmic collision. But we're not alone in this journey. Our galaxy belongs to what astronomers call the local group, a gravitationally bound cluster of more than 54 galaxies, all performing an intricate cosmic dance. The local group spans roughly 10 million light-years across. To put that in perspective, if our Milky Way were the size of a dinner plate, the local group would stretch from New York to Los Angeles. Within this vast neighborhood, three galaxies dominate everything else through their massive gravitational pull. The largest is the Andromeda Galaxy, containing over 1 trillion stars and stretching 220,000 light-years across. That makes it roughly twice the size of our own galaxy and heading straight toward us at 68 miles per second. The collision is confirmed to happen in approximately 4.5 billion years, but more on that cosmic catastrophe later. Our Milky Way ranks second in the local group hierarchy, with an estimated 300 billion stars spread across 100,000 light-years. We're currently positioned about 26,000 light-years from the galactic center, safely tucked away in what's called the Orion Arm, one of several spiral structures that gives our galaxy its distinctive pinwheel shape. The third major player is the Triangulum Galaxy, a spiral galaxy about half our size, containing roughly 40 billion stars. While smaller than its two massive neighbors, Triangulum is notable for having one of the highest rates of star formation in the local group, birthing new suns at nearly twice the rate of the Milky Way. But these three giants are surrounded by dozens of smaller satellite galaxies, many of which orbit our own Milky Way like cosmic pets. The largest of these satellites are the Large and Small Magellanic Clouds, visible to the naked eye from the southern hemisphere as fuzzy patches of light. The Large Magellanic Cloud contains about 30 billion stars, while its smaller companion hosts roughly 3 billion. What's fascinating is that this entire local group structure is itself just a tiny speck within an even larger cosmic architecture. We're located on the outer edge of something called the Laniakea supercluster, a collection of roughly 100,000 galaxies spanning 520 million light-years. The name Laniakea means immense heaven in Hawaiian, and it's our true cosmic address. All of these galaxies, including our own, are flowing like water toward a mysterious gravitational anomaly called the Great Attractor. This cosmic monster, located roughly 250 million light-years away, has the mass of tens of thousands of galaxies and is pulling our entire local group toward it at over 1,000 miles per hour. Yet even as we're being drawn toward this distant attractor, the expansion of space itself is simultaneously pushing most other galaxy groups away from us. It's like being on a cosmic treadmill, where some destinations get closer while others recede forever. But the peaceful appearance of our local group neighborhood masks a violent reality that's been unfolding for billions of years. The Milky Way is a monster that's been eating its neighbors alive for over 10 billion years. Right now, as you read this, our galaxy is in the process of violently tearing apart and consuming at least two smaller galaxies. The Sagittarius Dwarf Elliptical Galaxy is being slowly shredded by our galaxy's gravitational field, leaving behind streams of stars that wrap around the Milky Way like cosmic spaghetti. Meanwhile, the Canis Major dwarf galaxy is so thoroughly destroyed that astronomers only discovered its remains in 2003. This process isn't gentle. Think of it like a massive whirlpool in the ocean encountering a small fishing boat. The dwarf galaxy gets stretched and twisted by tidal forces that are literally ripping individual stars away from their home galaxy and flinging them into the Milky Way's outer halo. Some of these stellar refugees will eventually settle into stable orbits around our galactic center, while others get ejected entirely into the dark void between galaxies. The evidence for this ongoing galactic cannibalism is written in the stars themselves. Astronomers can identify which stars originally belonged to destroyed galaxies by studying their chemical composition and orbital patterns. Stars from the Sagittarius dwarf, for example, have a distinctly different mix of heavy elements compared to stars born in the Milky Way. It's like cosmic forensics, allowing scientists to solve crimes that happened billions of years ago. But the Sagittarius dwarf won't go down without a fight. Its disruption is triggering waves of star formation throughout our galaxy's spiral arms. As the dwarf galaxy's gas clouds collide with material in the Milky Way's disk, they compress and heat up, creating stellar nurseries where new stars are born at an accelerated rate. In a twisted way, The death of one galaxy is feeding the birth of countless new stars in another. The large and small Magellanic Clouds are next on the menu. These two galaxies, visible to the naked eye from Earth's southern hemisphere, are currently about 160,000 light-years away from us. But they're not in stable orbits. Astronomers have confirmed that both Magellanic Clouds are on a collision course with the Milky Way, expected to be fully consumed within the next 2 billion years. When the large Magellanic Cloud finally merges with our galaxy, the event will be spectacular. The collision will trigger massive bursts of star formation, light up the night sky with brilliant nebulae, and potentially wake up the supermassive black hole at our galaxy's center, turning it into a quasar that outshines entire galaxy clusters. This galactic cannibalism isn't unique to the Milky Way. The Andromeda Galaxy has been even more aggressive in consuming its neighbors. Astronomers have identified the remains of at least 10 different dwarf galaxies in Andromeda's outer regions, and the evidence suggests it devoured most of them within the last few billion years. Some of these ancient meals are still visible as faint streams of stars stretched across hundreds of thousands of light-years. The process follows a predictable pattern throughout the universe. Larger galaxies grow by consuming smaller ones, which in turn had previously consumed even smaller systems. It's a cosmic food chain that's been operating since the first galaxies formed over 13 billion years ago. But this local cannibalism is nothing compared to the ultimate galactic collision that's already begun. In 4.5 billion years, the night sky will be on fire. The Andromeda Galaxy, our nearest large neighbor, is racing toward us at 68 miles per second. That might not sound fast compared to the speed of light, but at cosmic scales, it's like two freight trains barreling toward each other on the same track. The collision is inevitable, confirmed, and will completely reshape both galaxies in the most violent cosmic event our region of space has ever experienced. The Hubble Space Telescope settled the question definitively in 2012 by measuring Andromeda's sideways motion across the sky. For decades, astronomers knew the galaxy was approaching us, but they couldn't determine if it would be a direct hit or a near miss. Hubble's precise measurements revealed the terrifying truth. Andromeda is aimed directly at the Milky Way's heart. When galaxies collide, it's not like two solid objects smashing together. Remember, galaxies are mostly empty space. The average distance between stars is about 25 trillion miles, so the chance of any two stars actually hitting each other during the merger is essentially zero. Instead, what happens is far more dramatic and chaotic. The collision will unfold over hundreds of millions of years, beginning with the outer edges of both galaxies starting to warp and stretch. Massive tidal forces will fling entire star systems out of their home galaxies and into the dark void between them. Some of these ejected stars will carry their planets with them, creating orphan solar systems drifting forever through intergalactic space. As the two galactic centers draw closer, their supermassive black holes will begin a deadly spiral dance. The Milky Way's central black hole contains about 4 million times the mass of our Sun, while Andromeda's is significantly larger at roughly 100 million solar masses. When these monsters finally merge, they'll create gravitational waves so powerful they'll ripple through the fabric of space itself, detectable by civilizations billions of light years away. The merger will trigger the most spectacular fireworks show in cosmic history. Gas clouds from both galaxies will collide and compress, igniting massive bursts of star formation that will light up the combined system like a cosmic Christmas tree. New stars will be born at a rate 10 times faster than what we see in either galaxy today. Earth's fate during this collision depends on some cosmic luck. Computer simulations suggest there's roughly a 50% chance our solar system will be flung 3 times farther from the galactic center than we are now. There's also a 12% chance we'll be ejected from the merged galaxy entirely, sent wandering through the darkness between galaxy clusters. But here's the truly mind-bending part. If humanity still exists when this collision begins, we'll have front-row seats to watch it unfold over millions of generations. The night sky will gradually fill with new stars as Andromeda grows larger and brighter. Eventually, it will dominate the entire sky, a spiral of fire stretching from horizon to horizon. The final product of this cosmic catastrophe will be a giant elliptical galaxy that astronomers have already nicknamed Milky Way. It will be roughly 10 times more massive than either original galaxy and will rank among the largest galaxies in our local supercluster. But even this ultimate collision pales in comparison to galaxies that have already died in ways that shouldn't be possible. There are galaxies out there that have been dead for billions of years, and scientists have no idea how they died. MAX 2129-1 looks like a perfectly normal spiral galaxy from a distance. It spins twice as fast as the Milky Way and contains several times more mass. But when astronomers looked closer, they discovered something that breaks every model of galaxy evolution we have. This galaxy stopped forming new stars over 10 billion years ago, making it a cosmic zombie that challenges everything we thought we knew about how galaxies live and die. Dead galaxies, or quenched galaxies, as astronomers call them, are systems where star formation has completely shut down. In a normal galaxy like ours, massive clouds of gas and dust constantly collapse under their own gravity to birth new generations of stars. The process should continue for trillions of years until the universe itself expands so much that galaxies can no longer hold onto their gas supplies. But MAX 2129-1 defied this natural order. Somehow, when the universe was less than a quarter of its current age, this galaxy exhausted or expelled all of its star-forming material. The problem is that according to our best models, this should be impossible for a galaxy of its size and type. Small galaxies can be quenched relatively easily. A nearby supernova explosion or the gravitational influence of a larger galaxy can strip away their gas supplies, effectively sterilizing them. But massive spiral galaxies like MAX 2129-1 should have enough gravitational pull to hold onto their gas, no matter what cosmic violence occurs around them. The discovery gets even stranger when you examine the galaxy's internal structure. Most dead galaxies that astronomers have found are elliptical shaped, resembling cosmic footballs, with stars distributed roughly evenly throughout. These shapes make sense because they form when two spiral galaxies collide and merge, scrambling their organized structure into a random blob. But MAX 2129-1 maintained its spiral structure even as it died. The galaxy's stars are still arranged in elegant curved arms radiating out from a central bulge, exactly like a living spiral galaxy. It's like finding a perfectly preserved mummy that looks completely alive from the outside, but contains no spark of life within. Even more puzzling, spectroscopic analysis reveals that the stars in this dead galaxy didn't form through the violent mergers that astronomers expected. Instead, they appear to have formed early in the galaxy's history through normal, peaceful star formation processes. Then something catastrophic happened that shut down all star formation almost instantly on cosmic timescales. Several theories attempt to explain this mystery, but none are fully satisfactory. One possibility is that the galaxy's central supermassive black hole went through an extremely active phase, generating powerful jets and radiation that heated up all the surrounding gas to the point where it could no longer collapse into stars. Another theory suggests that the galaxy experienced a series of massive supernova explosions that collectively blew away its entire gas supply. The most disturbing possibility is that we're missing something fundamental about how galaxies evolve. MAX 2129-1 might represent a completely unknown process that can kill even the largest, most robust galaxies without warning. And this dead galaxy isn't alone. Astronomers have now identified dozens of similar systems scattered throughout the distant universe, all massive spiral galaxies that somehow died billions of years before they should have. Each discovery adds another piece to a cosmic puzzle that seems to grow more mysterious rather than clearer. But dead galaxies are just the beginning of the cosmic weirdness waiting in the depths of space. Some galaxies are being torn apart so violently that they look like jellyfish swimming through a sea of stars. ESO 137-001, located 220 million light-years away in the constellation Triangulum Austral, is caught in the act of being destroyed. The galaxy appears to be swimming through space, trailing long tentacles of gas and stars behind it like a cosmic jellyfish. But this isn't a peaceful swim through empty space. This galaxy is drowning. The destruction is caused by a process called ram pressure stripping, and it's one of the most violent ways a galaxy can die. Imagine driving a convertible at highway speeds through a torrential downpour. The wind doesn't just get you wet, it strips the rain right off your windshield and flings it backward. Now scale that up to cosmic proportions. ESO 137-001 is racing through the Perseus galaxy cluster at over 1,000 miles per second. The space between galaxies in this cluster isn't empty. It's filled with extremely hot gas, heated to temperatures of over 100 million degrees Fahrenheit. This gas is so thin that it would count as a perfect vacuum by Earth standards. But when you're moving through it at cosmic speeds, it becomes like hitting a brick wall. The ram pressure from this hot intergalactic medium is literally stripping away ESO 137-001's own gas supplies. The galaxy's outer layers are being peeled off like the skin of an onion, creating spectacular trails that stretch for over 200,000 light-years behind the galaxy. These trails contain enough material to form billions of new stars. But instead of fueling the galaxy's growth, this precious star-forming gas is being scattered into the void. What makes the imagery even more striking is that the stripped gas doesn't just disappear. As it gets torn away from the galaxy, it forms intricate structures that really do resemble the tentacles of a jellyfish. These tentacles are illuminated by the ultraviolet radiation from young, hot stars that are still forming within the stripped material, creating an eerie blue glow against the darkness of space. The process is irreversible and ultimately fatal. Once a galaxy loses its gas supplies, it can no longer form new stars. The existing stars will continue to shine for billions of years, but gradually the galaxy will fade as its most massive stars burn out and explode as supernovae. Eventually, only dim red dwarf stars will remain, turning the once vibrant galaxy into a cosmic ghost. Astronomers have identified dozens of these jellyfish galaxies throughout nearby galaxy clusters, and each one tells the same tragic story. They're all caught in different stages of the stripping process, from galaxies just beginning to lose their outer gas layers to systems so thoroughly destroyed that only faint tentacles remain of what was once a thriving stellar metropolis. The Hubble Space Telescope has captured some of the most dramatic images of this destruction in action. In cluster after cluster, galaxies appear to be racing away from their own scattered remains, leaving trails of star formation in their wake like cosmic contrails. Some of these trails are so long and thin that they stretch across distances larger than our entire local group. But the violence doesn't stop with gas stripping. The same ram pressure that tears away a galaxy's star-forming material also disrupts its internal structure. Spiral arms get compressed and twisted, triggering bursts of star formation just before the gas supply is cut off forever. It's like watching a flower bloom just as it's being uprooted. The most haunting aspect of jellyfish galaxies is what they represent: cosmic beauty born from cosmic violence. These systems are among the most photogenic objects in the universe, with their streaming tentacles and bright blue star forming regions creating images that belong in an art gallery. Yet, each jellyfish galaxy represents the death throes of a cosmic civilization that might have harbored billions of worlds. But even the violent destruction of jellyfish galaxies seems normal compared to galaxies that challenge our most basic understanding of reality itself. There's a galaxy out there that shouldn't exist, and its very presence is breaking our understanding of how the universe works. NGC 1277 contains virtually no dark matter, which is like finding a skeleton without bones. Dark matter makes up roughly 85% of all matter in the universe and provides the invisible scaffolding that allows galaxies to form and maintain their structure. Without it, galaxies should either fly apart or never form in the first place. Yet, NGC 1277 is sitting there in space, apparently held together by nothing but the gravity of its visible stars. This discovery sent shockwaves through the astronomical community when it was announced in 2018. For decades, the existence of dark matter has been considered one of the fundamental pillars of modern cosmology. We can't see it, we can't touch it, and we don't know what it's made of. But we know it's there because its gravitational effects are visible everywhere we look in the universe. Dark matter acts like an invisible glue that holds galaxy clusters together. It's what allows spiral galaxies to spin without flying apart. It's what creates the cosmic web of filaments that connects all the large-scale structures in the universe. Without dark matter, the cosmos would look completely different if it could exist at all. NGC 1277 is what astronomers call a relic galaxy, meaning it formed early in cosmic history and has remained largely unchanged for billions of years. It's several times more massive than the Milky Way and packed into a much smaller volume, making it incredibly dense compared to modern galaxies. But despite containing hundreds of billions of stars, measurements show it has virtually no dark matter halo surrounding it. The initial discovery was controversial because it seemed to violate everything astronomers thought they knew about galaxy formation. Several teams of scientists double-checked the measurements, looked for errors in the data, and proposed alternative explanations. Maybe the galaxy was actually closer than originally thought, which would change the mass calculations. Maybe it had been somehow stripped of its dark matter by interactions with neighboring galaxies. But follow-up observations with multiple telescopes confirmed the impossible. NGC 1277 really does appear to be a massive galaxy with little to no dark matter. The finding was so significant that it required scientists to seriously reconsider some of their most basic assumptions about how the universe works. One proposed explanation is that NGC 1277 formed through an extremely rare process where normal matter was somehow separated from dark matter during the galaxy's birth. This could happen if the galaxy formed from material that had been heated to such extreme temperatures that the dark matter and normal matter behaved differently, allowing them to separate. Another possibility is that the galaxy's dark matter was stripped away by gravitational interactions with the massive Perseus galaxy cluster, where NGC 1277 resides. The cluster's enormous gravitational field might have been able to pull away the galaxy's dark matter halo while leaving the more tightly bound normal matter behind. But the most disturbing possibility is that our entire understanding of dark matter is fundamentally flawed. Maybe what we interpret as dark matter is actually a modification to the laws of gravity that behaves differently under certain conditions. If that's true, then NGC 1277 might be showing us what galaxies look like when this modified gravity effect is somehow turned off. The discovery has opened up new questions that astronomers are rushing to answer. Are there other galaxies like NGC 1277 hiding in the universe? Could entire regions of space exist where dark matter is absent? And what does this mean for our understanding of how structure formed in the early universe? What's certain is that NGC 1277 represents a cosmic anomaly that challenges everything we thought we knew about reality. But if galaxies without dark matter seem impossible, wait until you see galaxies where the gas shines brighter than the stars themselves. There's a galaxy in the early universe where the gas clouds are shining brighter than all the stars combined, and scientists are calling it totally new phenomena. GS-NDG-9422 exists from a time when the universe was only 1 billion years old, less than 10% of its current age. When astronomers first looked at its spectrum of light, they found something that had never been seen before: the signature of superheated gas that was actually outshining the galaxy's entire stellar population. In normal galaxies, stars are by far the brightest objects. They're nuclear fusion reactors that convert matter into energy at temperatures of millions of degrees, pumping out enormous amounts of light across all wavelengths. The gas between stars, while important for forming new stars, typically glows much more faintly and only shows up in specific narrow wavelengths. But GS-NDG-9422 flips this relationship completely upside down. The galaxy's gas clouds are being heated to over 140,000 degrees Fahrenheit, nearly twice as hot as the surface of typical massive stars. At these extreme temperatures, the gas becomes so energetic that it outshines the very stars that are supposed to be heating it. The discovery came from the James Webb Space Telescope's infrared spectrograph, which can break down the light from distant galaxies into its component wavelengths like a cosmic prism. When lead researcher Alex Cameron first examined the data, his reaction was immediate. That's weird. It was exactly the kind of totally new phenomena that Webb was designed to find in the early universe. The spectrum showed clear signatures of highly ionized gas, meaning the atoms in these clouds have been stripped of most of their electrons by intense radiation. This level of ionization requires an enormous input of energy, far more than what the galaxy's observed stars should be able to provide. It's like finding a pot of water boiling furiously over a candle flame. Working with theorist Harley Katz, the team developed computer models to explain what could create such extreme conditions. Their conclusion suggests that GS-NDG-9422 contains stars that are much hotter and more massive than anything we see in the local universe today. These primordial monsters might reach temperatures of over 140,000 degrees Fahrenheit at their surfaces, making them incredibly efficient at pumping out ultraviolet radiation. The implications extend far beyond just one weird galaxy. This gas outshining phenomenon might represent a missing link in our understanding of how the universe evolved from its dark ages into the star-filled cosmos we see today. During the first few 100 million years after the Big Bang, the universe was filled with neutral hydrogen gas that blocked most light from traveling very far. Something had to ionize all that hydrogen to make the universe transparent, and astronomers have long suspected it was the first generation of stars. But regular stars don't seem capable of producing enough ultraviolet radiation to do the job. Galaxies like GS-NDG-9422, with their superheated gas and ultra-massive stars, might be showing us exactly how cosmic reionization is more massive than our Sun and to have lived very brief, violent lives. GS-NDG-9422 provides the first observational evidence that such extreme stellar populations might have actually existed. But even this weird early galaxy seems almost normal compared to the massive systems that somehow assembled impossibly early in cosmic history. The James Webb Space Telescope has found galaxies that are so massive and formed so early that they're breaking our models of how the universe should work. 3 galaxies, nicknamed the Red Monsters, contain as much mass as our entire Milky Way, but they existed when the universe was less than 1 billion years old. That's like finding a fully grown adult at a preschool. According to our best theories of galaxy formation, these massive systems shouldn't have had enough time to assemble so early in cosmic history. The Red Monsters get their name from their distinctive appearance in Webb's infrared images. They glow with a deep red color because they're packed with dust, which absorbs blue and ultraviolet light from their stars and re-emits it as infrared radiation. This dust content is itself another mystery, because dust grains form from heavy elements that are produced inside stars over multiple generations. How did these early galaxies accumulate so much dust so quickly? Galaxy formation in the early universe was supposed to be a gradual process. According to the Standard Model, small clumps of dark matter slowly grew larger through gravitational attraction, eventually becoming massive enough to trap gas and begin forming stars. This process should take billions of years to create galaxies as large as the Milky Way. But the red monsters appear to have compressed this entire evolutionary sequence into less than 1 billion years. They're forming new stars at nearly twice the rate of similar mass galaxies today, suggesting that star formation in the early universe was far more efficient than our models predict. The discovery came from the FRESCO survey, which uses Webb's near-infrared camera combined with a GRISM spectrograph to measure precise distances and masses of early galaxies. Out of hundreds of galaxies studied, these 3 red monsters stood out as clear outliers that demanded explanation. What makes the finding even more puzzling is that these massive galaxies seem to be converting a much higher percentage of their available gas into stars than should be possible. In normal galaxy formation, supernova explosions and radiation pressure from massive stars blow away most of the gas that could potentially form stars. This feedback mechanism prevents galaxies from becoming too massive too quickly. But somehow the red monsters overcame this natural limitation. They managed to hold onto their gas supplies and convert them into stars with unprecedented efficiency. It's like finding a factory that operates at 200% capacity without any of the usual problems that should shut it down. The implications extend beyond just these 3 galaxies. If massive galaxies could form this efficiently in the early universe, it suggests that the cosmic environment 1 billion years after the Big Bang was fundamentally different from what we see today. Maybe the intergalactic medium was denser, making it easier for galaxies to accrete material. Maybe supernova feedback was less effective at early times. Or maybe our understanding of dark matter and galaxy formation is missing crucial pieces. The red monsters might be telling us that there are physical processes operating in the early universe that we haven't discovered yet. Each red monster contains roughly 300 billion stars, comparable to the total stellar mass of the Milky Way. But they're packed into much smaller volumes, making them incredibly dense compared to modern galaxies. Their central regions probably contain stellar densities thousands of times higher than what we see in our galactic neighborhood. The discovery of the red monsters represents what researchers are calling a too many, too massive problem. Not only did these individual galaxies grow larger than expected, but there are too many of them scattered throughout the early universe. Our models predict that such massive early galaxies should be extremely rare, yet Webb is finding them everywhere it looks. This abundance of early, massive galaxies is forcing astronomers to reconsider some of their most basic assumptions about cosmic evolution. But even the red monsters pale in comparison to the most distant galaxy ever discovered. A cosmic time machine that takes us back to when the universe was barely out of its infancy. We are looking at the most distant object ever discovered by humanity, and it existed when the universe was only 280 million years old. The galaxy designated MAMZ 14 represents the ultimate time machine, showing us conditions when our cosmos was barely 2% of its current age. The light reaching us today from this cosmic infant began its journey over 13.5 billion years ago, when the first stars were just beginning to illuminate a universe that had been dark for hundreds of millions of years. MAMZ 14 earned its nickname as the mother of all early galaxies because it shattered the previous distance record by 20 million years. That might not sound like much, but in the context of the early universe, 20 million years represents a significant fraction of the total time that had elapsed since the Big Bang. The galaxy's discovery required pushing the James Webb Space Telescope to its absolute limits, Even with Webb's unprecedented infrared sensitivity, MOMS C14 appears as just a few pixels of reddish light against the cosmic background. But those pixels contain information that has traveled farther through space and time than any signal humanity has ever detected. The extreme distance means we're seeing MOMS Z14 at a redshift of Z equals 14.44. Redshift measures how much the expansion of the universe has stretched the wavelengths of light during its journey to us. A redshift of 14.44 means the galaxy's light has been stretched by a factor of over 15, moving even its ultraviolet emissions into the infrared wavelengths where only Webb can detect them. What makes MOMS Z14 even more remarkable is that it's not just distant, it's also surprisingly massive and bright for such an early galaxy. The system contains several 100 million times the mass of our Sun, all packed into a region spanning roughly 1,600 light-years across. That's incredibly compact compared to modern galaxies, suggesting that star formation in the early universe was much more concentrated and intense. The galaxy appears to be in the midst of a furious burst of star formation, creating new suns at a rate that would build the equivalent of our entire solar system every few years. This level of activity produces so much ultraviolet radiation that it ionizes the surrounding gas, creating a bubble of transparency in what was otherwise an opaque universe. The discovery of MOMS Z14 came through the Mirage or Miracle survey, which uses Webb's spectrograph to confirm whether candidate early galaxies are really as distant as they appear or are actually nearby imposters reddened by dust. The survey got its name because finding bright galaxies so early in cosmic history would be either a mirage created by observational errors or a miracle that challenges our understanding of cosmic evolution. MOMS Z14 proved to be a genuine miracle. Spectroscopic analysis confirmed its extreme distance and revealed that the galaxy contains surprisingly heavy elements for such an early system. The presence of oxygen and other metals indicates that multiple generations of massive stars had already lived and died by the time we're seeing this galaxy, suggesting that star formation began even earlier than we thought possible. The galaxy's existence raises profound questions about how structure formed in the early universe. Current models predict that it should have taken longer for dark matter halos to grow massive enough to host such bright galaxies. MOMS Z14 suggests either that galaxy formation was more efficient than we realize, or that the early universe contained physical processes we haven't yet discovered. Perhaps most mind-boggling is the realization that we're seeing MOMS Z14 as it appeared when the universe was still emerging from its cosmic dark ages. This was an era when most of space was filled with neutral hydrogen gas that blocked light from traveling very far. The galaxy we're observing existed at the very beginning of cosmic reionization, when the first stars began clearing away this primordial fog. But MOMS Z14 is just one member of a growing population of early galaxies that are rewriting the story of cosmic dawn. Every photon of light from these primordial galaxies is a time traveler that began its journey when the universe looked nothing like it does today. The epoch between 200 million and 1 billion years after the Big Bang represents the most dramatic transformation in cosmic history. This era, called Cosmic Dawn, witnessed the birth of the first stars, the formation of the first galaxies, and the complete restructuring of all the matter in the universe, from a dark, neutral fog into the transparent, star-filled cosmos we see today. Before Cosmic Dawn, the universe was literally dark. No stars existed to produce light. The cosmic microwave background radiation had cooled below visible wavelengths, leaving space filled with nothing but invisible neutral hydrogen gas and mysterious dark matter. If you could somehow travel back to this time, you wouldn't be able to see your hand in front of your face, no matter how powerful your flashlight. But hidden within this darkness, gravity was slowly assembling the first structures. Tiny variations in the density of dark matter, imprinted during cosmic inflation just after the Big Bang, grew larger over millions of years. These dark matter halos eventually became massive enough to trap the surrounding hydrogen gas, creating the raw material for the first stars. The very first generation of stars, known as population 3 stars, were unlike anything that exists today. With no heavy elements available except what was created during Big Bang nucleosynthesis, these primordial giants formed from pure hydrogen and helium. Computer models suggest they were monsters, containing hundreds of times more mass than our Sun and burning at temperatures hot enough to synthesize the first carbon, oxygen, and iron in the universe. These stellar behemoths lived fast and died young, exploding as hypernovae after just a few million years. Their deaths seeded the surrounding space with heavy elements, allowing the second generation of stars to form with more diverse chemistry. It was this second generation that began assembling into the first true galaxies. The James Webb Space Telescope is giving us our first direct glimpses of cosmic dawn by detecting galaxies from this crucial epoch. Each discovery is like finding a fossil from the early universe, preserving conditions that existed over 13 billion years ago. These galaxies are so distant that we're literally seeing them as they were when the universe was still a cosmic infant. What's emerging from Webb's observations is a picture of cosmic dawn that's far more violent and chaotic than astronomers expected. The early galaxies are more massive, more active, and more numerous than our models predicted. Star formation rates in these systems are off the charts, suggesting that the first billion years of cosmic history were characterized by incredibly rapid and efficient galaxy assembly. The light from these primordial galaxies also carries information about the process of cosmic reionization. As the first stars began pumping out ultraviolet radiation, they gradually ionized all the neutral hydrogen in the universe, making space transparent for the first time since the cosmic microwave background was released 380,000 years after the Big Bang. This reionization process wasn't uniform. It began around the most massive early galaxies and slowly spread outward, creating bubbles of ionized gas that eventually merged to encompass the entire universe. Webb can actually map this process by studying how the light from distant galaxies is absorbed by intervening neutral hydrogen. Each new galaxy discovered from cosmic dawn adds another piece to this puzzle. We're learning that the transition from darkness to light happened faster and more dramatically than anyone imagined. The universe went from being completely dark to hosting massive, bright galaxies in less than 1 billion years, a cosmic transformation that ranks among the most important events in the history of everything. But these individual early galaxies were just the beginning of much larger cosmic violence that would reshape entire regions of space. 2 galaxies have been locked in a cosmic death spiral for over 600 million years, and we're watching the final act of their violent ballet. The antennae galaxies, officially designated NGC 4038 and NGC 4039, are located 68 million light-years away in the constellation Corvus. They earned their nickname from the spectacular tidal tails that stretch out from their distorted cores, like the antennae of some cosmic insect. But these aren't gentle appendages. They're streams of stars, gas, and dark matter being violently torn from their parent galaxies by gravitational forces that dwarf anything we can imagine. This collision began around 600 million years ago, when the 2 spiral galaxies first began to feel each other's gravitational influence. At that time, both were probably beautiful, well-ordered spiral systems similar to our own Milky Way. But as they drew closer together, their mutual gravity started to distort their shapes, pulling stars and gas into long streamers that now stretch over 200,000 light-years into space. The violence of this encounter is difficult to comprehend. Each galaxy contains hundreds of billions of stars, and all of them are being gradually accelerated and flung around by gravitational forces millions of times stronger than anything our solar system experiences. Some stars are being ejected entirely from both galaxies, destined to wander alone through intergalactic space for billions of years. But the most spectacular part of this cosmic collision is the burst of star formation it has triggered. When gas clouds from the two galaxies collide, they compress and heat up, creating ideal conditions for new stars to form. The antennae system is currently giving birth to new stars at a rate roughly 10 times higher than what we see in normal galaxies. These stellar nurseries are visible as brilliant blue and pink regions scattered throughout the collision zone. The blue areas mark clusters of hot, young stars that are pumping out enormous amounts of ultraviolet radiation. The pink regions show where this ultraviolet light is hitting surrounding gas clouds, causing them to glow like cosmic neon signs. The Hubble Space Telescope has revealed that the antennae collision is creating some of the most massive star clusters ever observed. These stellar metropolises contain millions of stars packed into regions just a few dozen light years across. If Earth were located near one of these superclusters, our night sky would be filled with thousands of stars brighter than Venus. Computer simulations show that the antennae galaxies are still approaching their moment of maximum violence. Over the next few 100 million years, their cores will spiral closer together, triggering even more intense bursts of star formation. Eventually, the two central supermassive black holes will merge in an event that will send gravitational waves rippling across the universe. The final product of this collision will be a single giant elliptical galaxy, larger and more massive than either of the original spirals. Most of the gas that currently fuels star formation will either be converted into new stars during the merger or blown away by supernova explosions, leaving behind a relatively quiet red system dominated by older stars. This transformation from spiral to elliptical is one of the fundamental processes that has shaped galaxy evolution throughout cosmic history. The antennae represent this process caught in the act, allowing astronomers to study exactly how galactic mergers unfold over hundreds of millions of years. What makes the antennae particularly valuable for research is that they're close enough for us to resolve individual star-forming regions and study the merger process in incredible detail. Astronomers can track how star formation rates change in different parts of the collision zone, measure the properties of the newly formed star clusters, and even detect individual supernova explosions within the chaos. The collision also serves as a preview of what will happen when our own Milky Way merges with the Andromeda Galaxy in 4.5 billion years. The physics involved will be essentially identical, though the Milky Way-Andromeda merger will be even more massive and spectacular than what we see in the antennae. But individual galaxy collisions, like the antennae, are just small-scale versions of much larger cosmic violence that plays out in galaxy clusters. In the richest galaxy clusters, smaller galaxies are being systematically tortured and destroyed by their more massive neighbors in a process astronomers call galactic harassment. The Coma cluster, located 320 million light-years away, contains over 1,000 galaxies packed into a region roughly 20 million light-years across. It sounds spacious, but at cosmic scales, this represents an incredibly dense concentration of massive objects, all moving at tremendous speeds through a shared gravitational environment. The result is cosmic chaos on an unimaginable scale. Galactic harassment occurs when galaxies experience repeated high-speed encounters with their neighbors over billions of years. Unlike the slow, intimate mergers we see between pairs of galaxies, harassment involves brief but violent gravitational interactions that gradually tear apart smaller systems without fully destroying them in a single encounter. Imagine a small galaxy as a carefully constructed sandcastle and the cluster environment as a beach during a hurricane. Each wave that hits the castle doesn't completely destroy it, but gradually erodes its structure, carrying away sand grain by grain until nothing recognizable remains. This is exactly what happens to galaxies in rich clusters, except the waves are gravitational forces from passing neighbors. The process is particularly devastating for spiral galaxies like our own Milky Way. Their delicate spiral arms and extended gas disks are easily disrupted by tidal forces from larger galaxies. During each harassment encounter, streams of stars get stripped away from the spiral arms, while ram pressure from hot intergalactic gas removes the cold gas needed for future star formation. The Hubble Space Telescope has captured dramatic images of harassment in action throughout the Coma Cluster. Galaxies appear distorted and stretched, with long tails of stars trailing behind them like cosmic contrails. Some systems are so thoroughly disrupted that they barely resemble galaxies at all, appearing more like shapeless clouds of stars scattered across hundreds of thousands of light years. One of the most striking examples is a galaxy designated NGC 4676, nicknamed the Mice because of its distinctive double-tail structure. This system started as two separate spiral galaxies that experienced a close encounter about 160 million years ago. The gravitational interaction stretched both galaxies into long, narrow shapes resembling the tails of mice, hence the nickname. But the mice represent just one moment in an ongoing process of destruction. Computer simulations show that these tidal tails will eventually be stripped away entirely, leaving behind two small, compact elliptical galaxies that will barely resemble their original spiral forms. The stars scattered in the tails will either be ejected into intergalactic space or eventually fall back to join one of the surviving galactic cores. The violence isn't limited to interactions between galaxies. The cluster environment itself is hostile to galaxy survival. The space between galaxies in rich clusters is filled with hot, tenuous gas, heated to temperatures of over 100 million degrees Fahrenheit. This intergalactic medium acts like a cosmic wind that strips away the cooler gas that galaxies need for star formation. The combined effect of harassment and gas stripping transforms the galaxy population in clusters over cosmic time. Rich clusters today are dominated by large elliptical galaxies and small, gas-poor systems called dwarf ellipticals. Very few large spiral galaxies survive in these environments, and those that do are usually found in the outer regions where the harassment is less intense. This cosmic violence has been operating for billions of years, fundamentally reshaping the galaxy population throughout the universe. Computer models suggest that most of the dwarf elliptical galaxies we see today in clusters are actually the remnants of larger spiral systems that were harassed into submission over cosmic time. But the destruction visible in galaxy clusters is just the tip of the iceberg compared to the invisible architecture that shapes everything we can see in the universe. Everything you can see in the universe is built on a foundation of something completely invisible. Dark matter makes up 85% of all matter in existence, yet it interacts with nothing except gravity. It doesn't emit light, it doesn't absorb light, and it doesn't reflect light. It's essentially the ghost of the cosmos, detectable only through its gravitational fingerprints on everything else. But without this invisible scaffolding, none of the galaxies we've been exploring could exist. Think of dark matter as the skeleton that gives shape to the cosmic body. Just as your bones provide the framework that allows your muscles and organs to maintain their structure, dark matter provides the gravitational framework that allows normal matter to clump together into stars, galaxies, and larger structures. Without it, the universe would be a smooth, featureless soup of gas with no structure at all. The evidence for dark matter is overwhelming and comes from multiple independent sources. When astronomers measure how fast stars orbit around galaxy centers, they find that the outer stars are moving much too quickly to be held in place by the gravity of visible matter alone. The galaxies should fly apart, yet they don't. Something invisible must be providing the extra gravitational pull needed to keep them intact. Galaxy clusters provide even more dramatic evidence. When the Coma Cluster was first studied in 1933, astronomer Fritz Zwicky calculated that the galaxies within it were moving so fast that the cluster should have dispersed billions of years ago. The only explanation was that the cluster contained far more mass than could be seen, hidden in some invisible form that Zwicky called dark matter. Modern techniques have allowed astronomers to actually map the distribution of dark matter throughout the universe using gravitational lensing. Massive concentrations of dark matter bend and distort the light from background galaxies, creating a cosmic funhouse mirror effect that reveals where the invisible matter is located. These maps show that dark matter forms a vast web-like structure spanning billions of light years. The cosmic web consists of dark matter filaments connecting massive nodes where galaxy clusters reside. Between these filaments lie enormous voids where very little matter of any kind exists. This web-like pattern provides the underlying architecture that determined where galaxies would form and how they would be distributed throughout space. On smaller scales, every galaxy sits at the center of a dark matter halo that extends far beyond the visible stars. Our own Milky Way is embedded within a dark matter halo that stretches at least 600,000 light-years from the galactic center, 3 times larger than the visible galaxy itself. This halo contains roughly 10 times more mass than all the stars and gas in the galaxy combined. Computer simulations show that, without dark matter, the universe would look completely different. The tiny density fluctuations that existed just after the Big Bang would never have grown large enough to form the first stars and galaxies. The cosmic microwave background would still show the same small temperature variations we observe today, but they would never have evolved into the rich tapestry of cosmic structure we see around us. Yet, despite decades of searching, scientists still have no idea what dark matter actually is. It could be composed of exotic subatomic particles that interact only through gravity. It could be primordial black holes left over from the early universe, or it could be something even stranger that we haven't imagined yet. What we do know is that this invisible foundation shapes absolutely everything else in the cosmos. But some regions of space contain dark matter structures so massive they harbor no visible light at all. Hidden throughout the universe are massive dark matter structures that contain no stars, no gas, and no light whatsoever. These dark galaxies represent some of the most mysterious objects in existence. They have enough mass to qualify as galaxies, containing billions of times the mass of our Sun, but they emit no light across any wavelength of the electromagnetic spectrum. They're essentially invisible cities of dark matter floating through the cosmic void, detectable only through their gravitational effects on nearby objects. The existence of dark galaxies was first predicted by computer simulations of cosmic structure formation. These models showed that while most dark matter halos should capture enough normal matter to form visible galaxies, some halos should remain dark, either because they formed in regions with very little gas, or because some process prevented normal matter from falling into them. Finding these invisible objects requires detective work on a cosmic scale. Astronomers look for their gravitational signatures by studying how they bend and distort light from background galaxies. When a dark galaxy passes between us and a more distant light source, its gravity acts like an invisible lens, creating telltale distortions that reveal its presence. One of the most compelling candidates for a dark galaxy is a massive structure discovered through gravitational lensing in the direction of the Virgo cluster. This invisible object contains roughly 1 billion times the mass of our Sun, but produces no detectable light at any wavelength. It's like finding a city-sized building that casts a shadow, but is completely invisible to every form of detection except its gravitational influence. The mystery deepens when you consider what could keep such massive dark matter halos from forming stars. In normal galaxy formation, dark matter halos capture surrounding gas through gravitational attraction. This gas cools and condenses into clouds that eventually collapse to form the first stars. Once star formation begins, the process becomes self-sustaining as new generations of stars continue to form from recycled material. Several theories attempt to explain how dark galaxies could avoid this fate. One possibility is that they formed in regions where the intergalactic gas was too hot to be captured by the dark matter halo's gravity. High-energy radiation from nearby galaxies or black holes could have heated the surrounding medium to temperatures where gas atoms move too quickly to be gravitationally bound. Another theory suggests that dark galaxies represent failed attempts at galaxy formation. Perhaps these halos began capturing gas and forming stars, but some catastrophic event stripped away all their normal matter before the process could be completed. Interactions with larger galaxies or passage through galaxy clusters could potentially remove all visible matter while leaving the dark matter halo intact. The most intriguing possibility is that dark galaxies represent a completely different evolutionary pathway that we don't yet understand. Maybe there are physical processes operating in certain environments that actively prevent normal matter from clustering within dark matter halos, creating these ghostly structures as a natural consequence of cosmic evolution. Recent observations with the James Webb Space Telescope are beginning to shed light on this mystery by detecting extremely faint galaxies that previous telescopes missed entirely. Some objects that were classified as dark galaxy candidates are turning out to be ultra-faint dwarf galaxies with just enough star formation to be barely detectable in infrared light. But other candidates remain completely dark despite Webb's unprecedented sensitivity. These confirmed dark galaxies challenge our understanding of the relationship between dark matter and normal matter in the universe. They suggest that galaxy formation is more complex and varied than our current models predict. The existence of dark galaxies also has profound implications for our census of cosmic structure. If significant numbers of galaxy-mass dark matter halos remain invisible, then we're dramatically underestimating the total amount of structure in the universe. What makes this even more mind-bending is realizing that these dark galaxies exist within an even larger invisible framework that connects every visible structure in the cosmos. Your cosmic address is far stranger and more vast than you could ever imagine. Most people know they live on Earth, in the solar system, in the Milky Way galaxy. But that's like saying you live in a house without mentioning the city, state, or continent. Your full cosmic address includes the local group, the Virgo cluster, and ultimately the Laniakea supercluster, a gravitationally connected structure containing over 100,000 galaxies spread across 520 million light-years. Laniakea wasn't discovered until 2014, which means humanity only recently learned the true scale of our cosmic neighborhood. The name means immense heaven in Hawaiian, and it's a fitting description for a structure so vast that light takes over 500 million years to cross from one end to the other. The discovery came from mapping the peculiar motions of galaxies throughout our region of space. While the expansion of the universe carries most galaxies away from each other, gravity also creates additional motions as galaxies are pulled toward massive concentrations of matter. By measuring these peculiar velocities, astronomers could trace the gravitational flows that define supercluster boundaries. What they found was astounding. The Milky Way, Andromeda, and tens of thousands of other galaxies are all flowing like water toward a massive gravitational attractor at the center of Laniakea. This great attractor region contains the mass of tens of thousands of galaxies and is pulling our entire cosmic neighborhood toward it at over 1,000 miles per hour. But Laniakea itself is flowing toward an even larger structure called the Shapley Attractor, located roughly 700 million light-years away. This creates a cosmic river of galaxies, all streaming in the same direction, across distances that dwarf our previous conception of large-scale structure. The Virgo cluster sits near the center of Laniakea and serves as the dominant gravitational influence in our cosmic region. This cluster contains over 2,000 galaxies, including several giant ellipticals that rank among the most massive galaxies in the known universe. The cluster's total mass is roughly 1,000 trillion times that of our Sun, making it one of the nearest examples of truly large-scale cosmic structure. Our local group, containing the Milky Way, Andromeda, and over 50 smaller galaxies, occupies a relatively quiet region on the outskirts of Laniakea. We're located in what astronomers call a cosmic suburb, far from the violent cluster environments where galaxy collisions and harassment are common. This peaceful location may have been crucial for allowing complex life to evolve on Earth. The structure of Laniakea reveals the cosmic web in action. Massive filaments of dark matter and galaxies connect the major galaxy clusters, while vast voids separate different regions of the supercluster. Our local group sits on one of these filaments, connected to the larger cosmic architecture, but isolated enough to avoid the destructive processes that occur in denser environments. What's truly mind-bending is realizing that Laniakea represents just one node in an even larger network of superclusters stretching across billions of light-years. The Perseus-Pisces supercluster, the Hydra Centaurus supercluster, and dozens of other massive structures create a cosmic web pattern that extends to the limits of our observable universe. Vast cosmic continent containing 100,000 galaxies, all connected by the invisible threads of gravity into a single, coherent structure. Yet, even this immense supercluster is just one small section of something far more vast and interconnected. The universe is built like a cosmic spiderweb, with massive filaments of dark matter and galaxies stretching across distances so vast they make entire superclusters look like tiny decorations. These galaxy filaments are the largest known structures in the universe, commonly reaching 50 to 80 megaparsecs in length. That translates to roughly 160 to 260 million light-years, distances so enormous that light from one end of a typical filament takes longer to reach the other end than complex life has existed on Earth. But some filaments are true cosmic monsters. The largest confirmed structure is called Hercules Corona Borealis Great Wall, stretching over 10 billion light-years across space. That's roughly 1/10 the diameter of our entire observable universe. If you could somehow travel at the speed of light, it would take you 10 billion years just to cross from one end of this structure to the other. These filaments form the backbone of cosmic architecture, connecting galaxy clusters and superclusters in a vast three-dimensional web that spans the entire universe. The pattern resembles a neural network or the internal structure of a living cell, with dense nodes connected by elongated strands and vast empty spaces between them. The cosmic web emerged from tiny quantum fluctuations that existed just after the Big Bang. During cosmic inflation, these microscopic variations in density were stretched to astronomical scales. Over billions of years, gravity amplified these small differences, causing matter to flow along the paths of least resistance between the densest regions. Dark matter led this cosmic construction project. Because it interacts only through gravity, dark matter could begin clustering as soon as the universe became cool enough for stable structures to form. Normal matter followed the dark matter's gravitational lead, flowing along the same pathways to create the galaxy filaments we observe today. The space between galaxies within these filaments isn't empty. It's filled with the warm, hot intergalactic medium, a tenuous gas heated to temperatures between 100,000 and 10 million degrees Fahrenheit. This gas is so thin that it barely qualifies as matter by Earth standards, but there's so much of it spread across such vast volumes that it contains more normal matter than all the stars in all the galaxies combined. Detecting these cosmic filaments requires sophisticated techniques because they're among the faintest structures in the universe. The gas within them is too thin and hot to emit much visible light, and the dark matter is completely invisible. Astronomers find them by mapping the distribution of galaxies and using computer simulations to trace the underlying dark matter web. One of the most successful detection methods uses gravitational lensing on massive scales. The combined gravitational field of dark matter within a filament can bend light from background galaxies, creating subtle distortions that reveal the filament's presence. Recent surveys have used this technique to map filaments connecting galaxy clusters across billions of light-years. The cosmic web profoundly influences galaxy evolution. Galaxies located within filaments have access to a steady supply of fresh gas flowing along the dark matter streams. This gas fuels ongoing star formation, allowing filament galaxies to remain active and continue growing for billions of years, longer than galaxies in other environments. Conversely, galaxies that end up in the spaces between filaments, called cosmic voids, gradually exhaust their gas supplies and fade into old, red systems, dominated by dying stars. The cosmic web literally determines which galaxies thrive and which ones wither away over cosmic time. The largest filaments contain thousands of galaxy groups and clusters, all flowing along the same cosmic highways. The local group, containing our Milky Way, sits on a relatively minor filament, connecting the Virgo cluster to more distant structures. But even this modest cosmic strand spans tens of millions of light years and influences the motion of every galaxy within it. Computer simulations show that the cosmic web will continue evolving for trillions of years as dark energy accelerates the expansion of space. Eventually, the expansion will become so rapid that it overcomes gravity, causing filaments to stretch and break apart. But for now, these cosmic superhighways continue to channel matter and energy across the largest scales imaginable, creating structures so vast they challenge human comprehension. Some structures in the universe are so mind-breakingly large that they shouldn't exist according to our models of cosmic evolution. The Sloan Great Wall stretches over 1.3 billion light-years across space, making it one of the largest known structures in the universe. To put this in perspective, if our entire observable universe were reduced to the size of Earth, the Sloan Great Wall would be roughly the size of North America. It contains tens of thousands of galaxies arranged in a sheet-like configuration that challenges our understanding of how structure could form on such enormous scales. But the Sloan Great Wall pales in comparison to the Hercules Corona Borealis Great Wall, a structure so massive that some astronomers question whether it can actually exist within our current cosmological models. This cosmic behemoth spans over 10 billion light-years, making it roughly 1/10 the size of the entire observable universe. These great walls represent the largest density enhancements in the cosmic web, regions where multiple galaxy filaments converge to create sheet-like structures containing millions of galaxies. They form the boundaries between vast cosmic voids, like the walls of enormous soap bubbles floating in space. The discovery of these massive structures came as a shock to cosmologists because they approach or exceed the theoretical maximum size that structures should be able to reach in our universe. According to the cosmological principle, matter should be distributed roughly uniformly on the largest scales. Structures like the Hercules Corona Borealis Great Wall test the limits of this fundamental assumption. The problem stems from how long it takes for gravity to build such massive structures. Even at the speed of light, it would take 10 billion years for gravitational influences to cross from one end of the Hercules Corona Borealis Great Wall to the other. Since the universe is only 13.8 billion years old, there shouldn't have been enough time for gravity to coordinate the formation of structure on such enormous scales. Yet these cosmic walls clearly exist, forcing astronomers to reconsider some of their basic assumptions about cosmic evolution. One possibility is that the early universe contained much stronger density fluctuations than we currently believe, providing larger seeds for structure formation. Another theory suggests that exotic physics during cosmic inflation could have created preferred directions in space, leading to enhanced structure formation along certain axes. The Great Walls also provide crucial insights into the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. The existence of such large structures places constraints on how dark energy behaves, because too much dark energy would prevent large-scale structure formation entirely. Galaxy surveys continue to discover new examples of these massive walls throughout the observable universe. The CFA-2 Great Wall, discovered in 1989, was the first structure recognized to span hundreds of millions of light-years. The Boss Great Wall, found in 2016, stretches over 1 billion light-years and contains some of the most distant galaxies ever observed. Each discovery adds to our understanding of the cosmic web's largest components. These walls aren't solid barriers, but rather enhanced regions of the web, where galaxy filaments cluster together. They contain billions of galaxies connected by dark matter filaments and separated by regions of cosmic void. The internal structure of great walls reveals the hierarchical nature of cosmic architecture. Within each wall, galaxies are organized into smaller groups and clusters, which in turn are connected by filaments spanning tens of millions of light years. It's like zooming into a fractal pattern where each level of magnification reveals similar organizational structures. Living within the cosmic web means that our entire observable universe represents just a small section of potentially infinite structure extending in all directions. The great walls we can observe might be just the local examples of patterns that repeat throughout an infinitely large cosmos. What makes this even more profound is the realization that these massive structures exist within ocean, like regions where almost nothing exists at all. Between the massive filaments and great walls lie regions of space so empty that they make the vacuum between stars look crowded by comparison. Cosmic voids are the largest empty spaces in the universe, spanning hundreds of millions of light years with almost no galaxies, stars, or even dark matter within them. These regions are so devoid of matter that if Earth were located in the center of a typical void, we wouldn't have discovered that other galaxies exist until the 1960s, and we'd still know about fewer than a dozen of them today. The Boötes void, also called the Great Nothing, exemplifies the extreme emptiness of these cosmic deserts. This spherical region spans roughly 330 million light-years in diameter, but contains almost no galaxies in its interior. If the Milky Way had formed in the center of the Boötes void, the nearest galaxy would be over 150 million light-years away, making it invisible to all but our most powerful telescopes. To understand just how empty these voids are, consider that the average density of matter throughout the universe is roughly 6 hydrogen atoms per cubic meter. That's already incredibly sparse by everyday standards. But within cosmic voids, the density drops to less than 1/10 of this universal average, creating regions that are emptier than the best vacuums we can create in laboratories on Earth. These voids didn't form through some cosmic explosion that cleared out the matter. Instead, they represent regions where the initial density of matter after the Big Bang was slightly lower than average. While gravity was pulling matter together to form filaments and galaxy clusters, these underdense regions became even emptier as their sparse matter was gravitationally attracted to the denser regions surrounding them. The process is still continuing today. Computer simulations show that cosmic voids are gradually expanding as the universe ages. Matter continues to flow out of these regions toward the surrounding walls and filaments, making the voids progressively larger and emptier over cosmic time. Eventually, voids will merge together to create even more enormous, empty regions. The few galaxies that do exist within cosmic voids are strange objects that challenge our understanding of galaxy formation. These void galaxies tend to be small, blue, and actively forming stars, characteristics that are unusual for galaxies in such isolated environments. They should have exhausted their gas supplies billions of years ago, yet many continue producing new stars at surprisingly high rates. One explanation is that void galaxies represent a different evolutionary pathway. Without the harassment and ram pressure stripping that affects galaxies in denser environments, void galaxies may be able to hold onto their gas supplies much longer than their counterparts in filaments and clusters. The largest known void is the Giant Void in the constellation Eridanus, spanning roughly 1 billion light-years across. This cosmic desert is so large that it contains several smaller voids within it, creating a hierarchical structure of emptiness that mirrors the hierarchical clustering of matter in the cosmic web. Living in a cosmic void would provide a profoundly different perspective on the universe. Instead of seeing thousands of galaxies scattered across the night sky, you'd see perhaps a handful of faint smudges representing the most massive galaxy clusters on the void's boundary. The universe would appear far more empty and desolate than the rich tapestry of stars and galaxies visible from our location within the cosmic web. Voids also play a crucial role in cosmic evolution by providing space for the universe to expand. As dark energy accelerates the expansion of space, voids grow larger, while the matter-filled regions become relatively more compressed. This process will continue for trillions of years, eventually creating a universe dominated by enormous empty regions separated by thin filaments containing all the remaining matter. The study of cosmic voids provides unique insights into dark energy and the large-scale structure of the universe. Because voids contain so little matter, their evolution is dominated by the expansion of space itself, making them natural laboratories for studying dark energy's effects on cosmic structure. But even these vast, empty regions exist within a universe where matter and energy are locked in constant warfare on every scale imaginable. Right now, 4 massive galaxy clusters are colliding in the most violent event our universe has witnessed since the Big Bang itself. The collision is taking place in Galaxy Cluster MAX J0717, located 5.4 billion light-years away. Each of the 4 clusters contains hundreds of galaxies and trillions of stars, plus enormous quantities of hot gas and dark matter. When objects this massive collide, they release more energy than the explosion of billions of supernovae happening simultaneously. This cosmic pileup represents the ultimate expression of gravitational violence in the modern universe. The clusters are approaching each other at speeds of thousands of miles per second, their mutual gravity accelerating quadrillions of tons of matter toward an inevitable rendezvous that will reshape an entire region of space. The Chandra X-ray Observatory has captured stunning images of this collision in progress, revealing the hot gas within each cluster, glowing at temperatures of over 100 million degrees Fahrenheit. As the clusters merge, their gas clouds collide and compress, heating the material to even more extreme temperatures and creating shock waves that propagate outward for millions of light years. But the most fascinating aspect of this collision is how it separates different types of matter through the violence of the impact. The hot gas in each cluster experiences friction and turbulence during the collision, causing it to slow down and lag behind. But the galaxies themselves, being much denser and more compact, pass through the collision zone with relatively little interaction. This creates a situation where the galaxies in each cluster become separated from their own hot gas, like runners leaving behind their shadows during a race. The dark matter in each cluster behaves similarly to the galaxies, feeling only gravitational forces and passing through the collision with minimal interaction. Gravitational lensing observations reveal the dark matter distribution during these cosmic crashes, showing how the invisible scaffolding of the universe responds to extreme gravitational stress. The dark matter halos of the colliding clusters stretch and distort as they interact, creating tidal forces that can strip away smaller satellite galaxies and fling them into intergalactic space. The energy released during major cluster collisions is so enormous that it heats the intergalactic medium across hundreds of millions of light-years. This heating can suppress galaxy formation throughout entire regions of space, by making it impossible for gas to cool and condense into new stars. Some cluster collisions create even more exotic phenomena. When 2 clusters with roughly equal masses collide head-on, they can pass through each other completely and then be pulled back together by their mutual gravity for a second collision. This process can repeat multiple times, creating a cosmic ping-pong ball effect that lasts for billions of years. The Bullet Cluster represents one of the most studied examples of this type of collision. 2 galaxy clusters collided at such high speed that their hot gas was completely separated from their galaxies and dark matter. The resulting configuration provided some of the strongest evidence for dark matter's existence, since gravitational lensing showed that most of the mass in the system was located with the galaxies rather than the hot gas. Computer simulations of cluster collisions reveal the incredible complexity of these events. The process unfolds over hundreds of millions of years, with multiple phases of approach, collision, separation, and recollision. Each phase triggers different types of physical processes, from shock heating of gas to tidal stripping of galaxies to the formation of massive radio-emitting structures. The violence of cluster collisions also triggers intense bursts of star formation, as gas clouds within galaxies are compressed by shock waves. Some of the most luminous galaxies in the universe are found in colliding clusters, powered by star formation rates hundreds of times higher than what we see in isolated galaxies. These cosmic battles represent the final stage of structure formation in our universe. As dark energy accelerates the expansion of space, galaxy clusters will become increasingly isolated from each other. The era of major cluster collisions will eventually come to an end, leaving behind a universe of isolated galaxy clusters separated by ever-expanding cosmic voids. But the violence visible in these collisions is just part of a larger cosmic ecosystem, where matter flows between structures in ways that were hidden from our view until very recently. Between every galaxy in the universe flows a cosmic river of gas, heated to temperatures that make the surface of the Sun seem cool by comparison. The intergalactic medium is filled with plasma heated to over 10 million degrees Fahrenheit, so hot that atoms are completely stripped of their electrons and exist as bare nuclei, swimming in a sea of free electrons. This material is so tenuous that it would count as a perfect vacuum by Earth standards, yet it contains more normal matter than all the stars in all the galaxies combined. These cosmic rivers follow the dark matter filaments that connect galaxy clusters, creating a circulatory system that transports matter and energy across billions of light years. Gas flows along these channels like blood through cosmic arteries, carrying the raw materials needed for galaxy formation from one structure to another. The temperature of this intergalactic gas seems impossibly high until you understand its origin. When matter falls into dark matter filaments under the influence of gravity, it gets compressed and heated, just like air gets hot when you pump up a bicycle tire. But at cosmic scales, this gravitational heating can raise temperatures to millions of degrees. Additional heating comes from supernova explosions within galaxies, which blast hot gas outward at speeds of thousands of miles per second. This superheated material joins the intergalactic flow, carrying heavy elements created in stellar cores out into the cosmic web, where they can eventually be incorporated into new generations of galaxies. The intergalactic medium is largely invisible to optical telescopes, because hot plasma doesn't emit much light at visible wavelengths. Instead, astronomers detect it using X-ray telescopes that can see the high-energy radiation produced when electrons in the plasma interact with the intense magnetic fields generated by galaxy clusters. Recent observations have revealed vast networks of hot gas connecting galaxy clusters across hundreds of millions of light years. The Planck satellite has mapped some of these connections by detecting the thermal Sunyaev-Zeldovich effect, which occurs when cosmic microwave background photons pass through hot plasma and get boosted to slightly higher energies. But the most dramatic discovery came from fast radio bursts, brief flashes of radio waves from distant galaxies that act like cosmic lighthouses, illuminating the intergalactic fog. As these radio pulses travel through space, they interact with free electrons in the intergalactic medium, creating a delay that depends on how much plasma the signal encountered along its journey. By studying hundreds of fast radio bursts, astronomers have confirmed that roughly half of all normal matter in the universe exists in this hot intergalactic state. This solved a decades-old mystery known as the missing baryon problem. Theoretical models predicted how much normal matter should exist based on observations of the cosmic microwave background, but astronomers could only account for about half of it by counting stars, gas, and other visible matter in galaxies. The missing baryons were hiding in plain sight all along, spread throughout the cosmic web as invisible rivers of superhot plasma. This discovery fundamentally changed our understanding of how matter is distributed throughout the universe. The intergalactic medium also plays a crucial role in galaxy evolution by regulating the flow of gas into and out of galaxies. Galaxies can capture fresh gas from these cosmic rivers to fuel new star formation, but they can also lose gas to the intergalactic medium through supernova-driven winds and other feedback processes. All the hydrogen in the universe, heating it to temperatures we still observe today. These cosmic rivers represent one of the most active areas of current astronomical research, as scientists work to understand how the intergalactic medium influences galaxy formation and evolution across cosmic time. But even this vast network of cosmic rivers represents just a fraction of the matter and energy that permeates apparently empty space. For decades, half of all the normal matter in the universe was missing, hidden in a cosmic fog so thin and hot that it was essentially invisible. The mystery began with precise measurements of the cosmic microwave background, the afterglow of the Big Bang that still permeates all of space. These observations revealed exactly how much normal matter, also called baryonic matter, was created during the first few minutes of cosmic history. The answer was definitive. Normal matter should make up about 5% of the universe's total mass energy. But when astronomers tried to find all this matter by counting stars, gas clouds, planets, and everything else they could observe, they came up short, way short. They could only account for about half of the normal matter that should exist. The rest had simply vanished from the cosmic census. This wasn't dark matter, which is an entirely different mystery involving exotic particles that don't interact with light. This was ordinary matter made of protons, neutrons, and electrons that should be detectable if astronomers knew where to look. But despite decades of searching with increasingly powerful telescopes, roughly half of all normal matter remained missing. The solution came from an unexpected source: fast radio bursts, brief flashes of radio waves from distant galaxies that last just milliseconds, but release more energy than our sun produces in an entire day. These cosmic beacons turned out to be perfect tools for detecting the invisible intergalactic fog that was hiding the missing matter. When fast radio burst signals travel through space, they interact with free electrons in the intergalactic medium. This interaction causes longer radio wavelengths to arrive at Earth slightly later than shorter wavelengths, creating a measurable delay that depends on how many electrons the signal encountered during its journey. By studying the dispersion of dozens of fast radio bursts from known distances, astronomers could calculate the total number of electrons along each line of sight. Since electrons come from ionized hydrogen, this measurement revealed the distribution of normal matter throughout the cosmic web. The results solved the missing baryon mystery definitively. The lost matter was hiding in plain sight as hot, ionized gas spread throughout the filaments connecting galaxy clusters. This warm, hot intergalactic medium is heated to temperatures between 100,000 and 10 million degrees Fahrenheit, making it extremely difficult to detect directly. The gas is so thin that a volume the size of Earth's atmosphere would contain less matter than a single breath of air. But there's so much space between galaxies that even this incredibly tenuous material adds up to enormous total mass when integrated across cosmic volumes. This discovery represented a triumph of 21st century astronomy, combining theoretical predictions, computer simulations, and observations across multiple wavelengths to solve a fundamental mystery about cosmic composition. It also demonstrated how the universe's matter budget is distributed. Roughly 5% exists as normal matter, with half in stars and galaxies and half in the hot intergalactic medium. The finding has profound implications for understanding galaxy evolution. The hot intergalactic medium serves as a reservoir of gas that galaxies can tap into for future star formation, but it's also heated to temperatures that make it difficult for galaxies to capture. This creates a cosmic thermostat that regulates how quickly galaxies can grow over time. Computer simulations now include the effects of this hot intergalactic medium when modeling how galaxies form and evolve. The results show that feedback between galaxies and the intergalactic medium is crucial for explaining the observed properties of galaxy populations throughout cosmic history. The discovery also highlights how much we still don't know about the universe's contents. While we've now accounted for normal matter, dark matter, and dark energy together make up 95% of everything that exists. These mysterious components remain almost completely unknown despite decades of intense research. What we do know is that this cosmic fog of missing matter permeates every corner of the observable universe, connecting all structures in an invisible web of superhot plasma. And that observable universe itself has boundaries that represent the ultimate frontier of human knowledge. In what appears to be the emptiest patch of sky imaginable, Hubble found 10,000 entire galaxies hiding in the darkness. The Hubble Ultra Deep Field required astronomers to commit telescope time that seemed almost wasteful. They pointed the Hubble Space Telescope at a tiny region of sky in the constellation Fornax that appeared completely empty to the naked eye. This patch of darkness was smaller than a grain of sand held at arm's length, yet Hubble stared at it for over 11 days, collecting 800 separate exposures to create the deepest image of space ever obtained. What emerged from those 11 days of observation changed our understanding of the universe forever. That apparently empty patch of sky revealed galaxies scattered like cosmic jewels across billions of years of cosmic time. Nearly every point of light in the image represents an entire galaxy containing billions of stars, planets, and potentially civilizations we'll never know about. The image serves as a cosmic time machine, with galaxies at different distances representing different epochs in cosmic history. The nearest galaxies appear as they were millions of years ago, while the most distant ones show us the universe when it was less than 1 billion years old. It's like viewing a family photo that spans 13 billion years of cosmic evolution. Some galaxies in the ultra-deep field are among the first ever formed cosmic pioneers that assembled when the universe was still emerging from its dark ages. These primordial systems appear small, irregular, and blue, packed with young stars and actively forming new ones at rates that dwarf anything we see in the modern universe. Other galaxies represent more mature systems that had billions of years to evolve into the elegant spiral and elliptical shapes we recognize today. The image captures galaxy mergers in progress, showing how cosmic violence has shaped galactic evolution over vast stretches of time. But perhaps the most profound revelation is what the ultra-deep field tells us about cosmic real estate. This tiny patch represents just 1/13 millionth of the entire sky. If every similar patch contains 10,000 galaxies, then the total number of galaxies in the observable universe reaches into the trillions. The follow-up observations went even deeper. The Hubble Extreme Deep Field combined data from multiple ultra-deep field campaigns to push even further back in time, revealing galaxies that existed when the universe was just 400 million years old. These cosmic babies show us galaxy formation in its infancy, when the first stellar nurseries were just beginning to light up the cosmic darkness. The James Webb Space Telescope has now surpassed even these remarkable achievements. Webb's infrared vision can detect galaxies that are completely invisible to Hubble, pushing the cosmic frontier back to just 280 million years after the Big Bang. Each new observation reveals more galaxies in what we thought were empty regions of space. What makes these deep field observations so powerful is their democratic nature. Unlike targeted observations of specific objects, deep fields show us the universe as it really is, with all types of galaxies represented according to their actual abundance. They provide an unbiased census of cosmic populations across the entire history of the universe. The images also reveal the cosmic web in action on the largest scales. Galaxies aren't randomly scattered through space, but follow the and transform them into compact ellipticals. The deep fields serve as laboratories for testing our theories of galaxy formation and evolution. By counting galaxies of different types at different cosmic epochs, astronomers can trace how the galaxy population has changed over billions of years and compare these observations with predictions from computer simulations. But even these deepest images show us only a tiny fraction of what exists beyond our cosmic horizon, where light from countless more galaxies will never reach us due to the expansion of space itself. There is an absolute wall in space beyond which we can never see, no matter how powerful our telescopes become. This cosmic horizon isn't created by a physical barrier or some mysterious force blocking our view. It exists because light itself has limits, and the universe hasn't existed long enough for photons from the most distant regions to reach us. At the edge of our observable universe lies the cosmic microwave background, the afterglow of the Big Bang itself, representing the last moment when the universe became transparent to light. The cosmic microwave background formed roughly 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, called recombination, the universe was filled with free electrons that scattered photons continuously, making space completely opaque like the interior of a star. When recombination occurred, photons were suddenly free to travel through space without being scattered. The cosmic microwave background represents this flash of liberation, the moment when the universe lit up for the first time. But here's the crucial point. We can't see anything that happened before this moment, because no light from earlier times can reach us. This creates a fundamental limit to observation that no technology can overcome. The cosmic microwave background forms an opaque wall that blocks our view of the universe's first 380,000 years. Behind this wall lie the cosmic dark ages, when the first stars were forming, but their light couldn't propagate through the neutral hydrogen fog that filled space. The observable universe extends roughly 46.5 billion light-years in all directions from Earth, giving it a diameter of about 93 billion light-years. This distance is larger than you might expect for a universe that's only 13.8 billion years old, because space itself has been expanding during the time it took light to reach us. Think of it like a cosmic conveyor belt. Light from the most distant galaxies began its journey when they were much closer to us, but the expansion of space carried those galaxies farther away while their light was traveling toward us. By the time we receive their photons, the galaxies themselves are much more distant than when they emitted the light we're seeing. This expansion also means that some galaxies we can currently observe are now beyond our future light horizon. We can see them because their light had time to reach us in the past, but any light they emit today will never arrive at Earth because the space between us is expanding faster than light can cross it. The cosmic microwave background provides a baby picture of the universe, showing tiny temperature fluctuations that represent the seeds of all future cosmic structure. These fluctuations, caused by quantum variations during cosmic inflation, eventually grew under gravity's influence to become the galaxies, clusters, and cosmic web we observe today. Modern satellites like Planck have mapped these fluctuations with extraordinary precision, revealing the universe's composition, age, and fate with remarkable accuracy. The patterns in the cosmic microwave background confirm that the universe is flat, composed of roughly 5% normal matter, 27% dark matter, and 68% dark energy. But the cosmic microwave background also tantalizes us with hints of what lies beyond our observational reach. The fluctuations we observe represent only the portion of primordial variations that were small enough to fit within our observable universe. Much larger variations likely exist beyond our cosmic horizon, potentially creating regions with fundamentally different properties. This raises profound questions about the nature of reality beyond our cosmic bubble. The actual universe may be infinite in extent, containing infinite copies of every possible configuration of matter and energy. Or it may be part of an infinite multiverse where different regions have different physical laws and constants. What we know for certain is that our observable universe represents just a tiny fraction of everything that exists. We are confined to a spherical bubble of observable space, surrounded by infinite mystery that we can never directly explore. Yet, even this limitation can't diminish the wonder of what lies within our cosmic horizon. Outside the boundaries of everything we can ever observe lies infinite mystery that dwarfs our observable universe beyond all comprehension. Within an infinite ocean of space containing infinite galaxies, infinite stars, and infinite copies of every possible configuration of matter. This isn't science fiction speculation. It's the logical consequence of our best understanding of cosmic geometry and the fundamental laws of physics. In an infinite universe, every possible arrangement of atoms must occur somewhere, including exact copies of Earth, the solar system, and even you reading these words right now. The mathematics are staggering. In a volume roughly 10 to the power of 10 to the power of 118 meters across, every possible quantum state of that volume would be exhausted, forcing exact repetition of everything within it. That means somewhere beyond our cosmic horizon, perhaps unimaginably far away, there's another planet identical to Earth, where another version of you is having exactly the same thoughts at exactly the same moment. But infinity contains more than just identical copies. It also contains every possible variation. There are versions of Earth where the dinosaurs never went extinct, where you made different life choices, where entire histories unfolded along completely different timelines. Every possibility that doesn't violate the laws of physics exists somewhere in infinite space. The implications extend far beyond just copied planets and people. Entire galaxy clusters, identical to our local group, exist infinitely many times throughout infinite space. There are infinite copies of the Milky Way, infinite versions of the Andromeda collision, infinite repetitions of every cosmic event we've discussed in this journey through the observable universe. Yet, infinity also ensures that genuine novelty exists beyond our horizon. Structures and phenomena that have never occurred within our observable universe must exist somewhere in infinite space. There could be galaxy clusters containing quadrillions of galaxies, black holes larger than our entire observable universe, or forms of matter and energy that operate according to physical laws we haven't discovered. The multiverse concept takes this even further. Cosmic inflation theory suggests that our entire universe might be just one bubble in an infinite multiverse, where different regions have different physical constants, different numbers of dimensions, and different fundamental forces. In this scenario, our observable universe would be like a single cell in an infinite organism of unimaginable complexity. Some regions of the multiverse might have stronger gravity, allowing stars to form from hydrogen gas much more efficiently. Others might have weaker electromagnetic forces, preventing atoms from forming stable molecules. Most regions would be sterile, incapable of supporting any form of complexity or life as we know it. But infinity ensures that every possible universe exists somewhere in the multiverse, including ones where the physical constants are fine-tuned for complexity beyond our wildest imagination. There could be universes where consciousness emerges naturally from vacuum fluctuations, where space and time have completely different structures, or where beings exist that are to us as we are to elementary particles. The existence of infinite space beyond our cosmic horizon also has profound implications for the nature of causality and free will. If every possible future already exists somewhere in infinite space, then are we choosing our path through reality, or simply discovering which pre-existing timeline we happen to be following? These questions push the boundaries of human comprehension and may be fundamentally unanswerable. We are finite beings trying to grasp the implications of infinity, limited observers attempting to understand unlimited reality. What we can say with confidence is that our observable universe, vast as it seems, represents an infinitesimally small fraction of everything that exists. We are residents of one tiny bubble in an infinite cosmic ocean, explorers of one small island in an endless archipelago of reality. Yet this limitation doesn't diminish the profound significance of what we've discovered within our cosmic bubble. After flying through 2 trillion galaxies across 13.8 billion years of cosmic history, we return to the most profound question of all. What does this mean for us? Every galaxy we've explored, from the most distant cosmic dawn infant to the massive present-day giants, formed through the same fundamental processes that created our own Milky Way. The carbon in your body was forged in the nuclear furnaces of massive stars that exploded billions of years ago. The oxygen you breathe came from stellar death throes that seeded space with heavy elements. You are literally made of star stuff that has been recycling through the cosmic web for eons. But the cosmic perspective reveals something even more profound. In a universe containing 2 trillion galaxies, each harboring hundreds of billions of stars isolated on our small blue world, this paradox defines the human condition in the 21st century. We've discovered our true place in a universe far grander and more violent than our ancestors could have imagined. We've learned that Earth orbits an ordinary star in the outer reaches of a typical galaxy. That's just one member of a modest galaxy group in an unremarkable region of a vast supercluster that itself is merely one node in an infinite cosmic web. From this perspective, every human conflict, every political boundary, every economic system seems almost absurdly small. Wars fought over patches of land on a single planet pale in significance compared to galaxy collisions that reshape entire regions of space over hundreds of millions of years. The rise and fall of civilizations becomes a brief flicker in the cosmic timeline that stretches from the Big Bang to the heat death of the universe trillions of years in the future. Yet, the cosmic perspective also reveals the extraordinary preciousness of what we have here on Earth. In a universe dominated by radiation, plasma, dark matter, and the violent extremes of stellar nucleosynthesis, planets capable of supporting complex chemistry and life are rare cosmic treasures. Earth represents billions of years of cosmic evolution concentrated into a single world where the universe became conscious of itself. We are the universe's way of knowing itself. Through human consciousness, the cosmos has developed the ability to contemplate its own existence, to trace its history from the first moments after the Big Bang to the present, and to predict its future evolution across unimaginable spans of time. Every telescope observation, every scientific discovery, every moment of cosmic wonder represents the universe looking at itself through our eyes. This realization carries profound responsibility. We are the only known beings capable of preserving and transmitting cosmic knowledge across generations. The story of the universe, from quantum fluctuations in the cosmic inflation to the formation of 2 trillion galaxies, exists in its full glory only within human consciousness and the scientific records we create. Our cosmic journey through every galaxy in the observable universe reveals that we live in an age of unprecedented discovery. Never before in human history have we been able to see so far into space and time, to understand so much about our cosmic origins and destiny, or to appreciate the true scale of the universe we inhabit. The James Webb Space Telescope and future observatories will continue pushing back the frontiers of knowledge, revealing new types of galaxies, new cosmic phenomena, and deeper insights into the fundamental nature of reality. Each discovery adds another piece to the cosmic puzzle, bringing us closer to answering the ultimate questions about our existence and purpose. Yet perhaps the most important lesson from our journey through 2 trillion galaxies is that the universe is far stranger, more beautiful and more awe-inspiring than we ever imagined. From dark matter scaffolding to galactic cannibalism, from impossible early galaxies to cosmic web filaments spanning billions of light years, reality consistently exceeds the limits of human imagination. We end where we began, as temporary arrangements of atoms in an infinite cosmos. But now, with the knowledge that we are participants in the most extraordinary story ever told, the evolution of the universe itself, from simplicity to complexity, from darkness to light, from unconscious matter to conscious beings capable of contemplating their own cosmic significance. In the end, flying through every galaxy in our observable universe brings us home to Earth with a deeper appreciation for both our cosmic insignificance and our cosmic importance. We are small, temporary, and isolated in space and time. But we are also the universe's greatest achievement, matter organized in such a way that it can understand its own existence and contemplate the infinite mystery that surrounds us on all sides.